serviceability, because we don't want beam, this beam to deflect excessively, excessively, because under loading it will deflect, but we don't want it deflect excessively. Therefore, we have to calculate if the deflection is more than allowable in the design standard or in the building design, then we have to enlarge the beam, change the beam, or to reduce the loading, or maybe to change the structural arrangement. Yeah, that's why we have to learn how to calculate the deflection of beam. Okay, so there are basically four method of calculation. Integration method, the use of discontinuity function or Macaulay method, which is actually modification of the integration method. We have another method is virtual work method or unit load method, which we have done in truss deflection. So we use the same concept of external load and internal load as we have done for truss analysis. And another method is moment array method, which I think we don't have enough time to present this moment array method. If you need to study this moment array method, maybe we have to do it in your self-learning. Okay. So as I mentioned, this is the deflection. This is experimental in a lab. Where you can see here full-scale testing concrete beam. About 20 meters span. So why we need to do experiment? Because we want to study, to compare between the theoretical and experimental. In theoretical we have a formula. But the formula, as we will see later, it depends on E and I, and also in material. E is material, Young's modulus. We have Young's modulus for concrete, Young's modulus for steel. But what is Young's modulus for reinforced concrete? You have not done reinforced concrete. This is the composite between concrete and steel. That's why we carry out experimental. Okay. This is just a revision. This is in first topic and also in previous topic on truss. Truss. We have seen that the stress. The elongation. The elongation is depends on E value, E and A. Deformation is equal to PA over L. Truss. This is called axial deformation. Deformation or axial deformation. We have shear deformation, axial deformation. For beam, we have another deformation, in the direction normal to the axis. This one deformation in the direction collinear with the axis. This one in the direction normal to the axis, where we call it deflection or bending deflection. And the governing factor, for the axial deformation, the governing factor is E and A, cross section and Young's modulus. But for deflection, the governing factor is E and I. I is the moment of inertia, moment of inertia, where I can be changed, when we change the orientation of the section. A, doesn't matter what orientation, the A is constant. So this is the difference between axial deformation and bending deformation, or we call it deflection. Okay. Yes. This is what happened, when we have excessive deflection. Excessive deflection, together with actually in this case buckling deflection, where the beam cannot afford to carry any more loading, then it deflect or rupture in case collapse. So we don't want this to be happen in our structure. Look at this one. This is not collapse. This is just excessive deflection. But what what you can see here is that this one is composite. This is concrete slab. Concrete slab. This one steel beam. When beam deflect excessively, there will be cracking in the concrete soffit or concrete slab or concrete floor. Why? Because it deflect excessively. So we don't want this to be happen, and we must control the deflection by calculating first what is the deflection. What's supposed to be the deflection? If from the calculation before the construction, the deflection is too much, then we have to enlarge the section. Okay. So what is this? Similar to axial deformation, deflection also controlled by E value. So if you have different material, at this elastic, area, deflection will be different, depend on this slope. This slope is called E. This slope is called Young's modulus. So we will have 4 type of material, and we'll have 4 value of E, and we will have 4 value of deflection. Okay. So even though the A and I is similar, is equal, but if E value is different, you will have different deflection. So that's why we have to be careful what the choice of material we want to use in our structure. So what happened, as I mentioned before, what happened if there is excessive deflection? This is our room, our room, our lounge room. This furniture, as you can see here, it is in good position here, because the slab is perfectly level. What happens is if the slab deflect, what happens? This furniture will move here and there. And what happens if the beam deflect? The floor here, the wall will crack, and the window cannot shut properly, and so many problems. So this is called serviceability limit. Serviceability checking. It is, the purpose is for the service. Because if it has excessive deflection, it is not in good service to us. That's why we have to control the deflection. Okay. Now we start with the theoretical calculation. So the deflection, the calculation is based on the principle of curvature. Principle of curvature. What is curvature? In the next slide. The deflection diagram of the longitudinal axis that passes through the centroidal each cross-section area of the beam is called curvature. This is curvature. It is called elastic curve. It is called elastic curve because it is still in elastic area here. We are now talking about this area, not this area. This area is called non-elastic. Or we call it plastic zone. Of course, we don't want our beam, our structure, to reach the plastic zone. Only in elastic zone. What is elastic? Elastic zone is when you unload or you remove this load, it will come back into the original position. It is called elastic. Okay, so this is simply supported. This one is simply supported here and rigid connection here. This one simply supported, but you have cantilever here. So this is just common sense. What's the shape is just common sense. Okay, so for the calculation, yeah, which will proceed later. Okay, uh, for the sign convention, this is positive moment, this one negative moment. Yeah, this is downward, it is upward. Just to take note, when we work with moment. This is the same as in your shear force and bending moment diagram. Okay, now back to curvature. So this is a portion of the beam. It's not the whole beam, a portion, very small portion. A portion can be, maybe if the beam is 6 meter, maybe the portion maybe 100, 100 millimeter, the portion. So actually, for a small portion, this R is very, very large, very large, and this angle is very, very small, and this slope is very, very small. When we say this is a portion, this slope is, this curve is very small. So what the significance of small? Okay, we'll see later. Why? Why we assume as small? Okay, look at this figure. Look at this figure. Yeah, A dash B dash, A dash B dash is the curvature or the length, the centroidal axis A dash B dash, and A dash B dash will not change whatever the curvature. What will change is the internal space here, the internal layer here, and the external. This one will change to shorter. This one will be changed to longer than the centroidal, the center line. This comes easy to understand. And what is the length of A dash B dash is equal to, but in this case, R is outer layer of the beam, and Y, Y is, we call it neutral axis depth of neutral axis. So, okay, if the neutral axis depth is Y, why? Because in your bending stress distribution, in the previous topic, we use Y. Okay, so R theta minus R minus Y. R minus Y. R minus Y is this one. R minus Y. This is R minus Y. Here, sorry. So R minus Y theta is equal to L dash. Okay. So, and this displacement delta to L minus L dash, displacement is not shown here. Displacement is actually strain, L minus L dash here. Is the bending strain equal to R theta minus R minus Y theta equal to Y theta, where Y is the depth of the neutral axis. Delta. Therefore, strain equal to delta over L equal to theta cancel theta y over r. And from this equation, we will have 1 over r equal to strain E epsilon divided by y. And this is a very useful equation. We will use this yeah, this is called Cauchy equation. R equal to E over y of epsilon of y. And yeah, uh, it is to note here in inelastic region. In inelastic region, E equal to region. Probably E sigma over force strain equals sigma of E. Elastic smallest of this curve. This is in elastic region. Okay. Therefore, uh, yeah, therefore, strain equal to stress divided by E. Sigma is stress. Okay. And this is another formula. Uh, Sigma is equal to my over I. I think you have come this before in ring distribution. In distribution, the formula that also very important, and we must memorize this formula. Memorize for sigma is Okay. Boleh dapat Boleh?
Boleh, Doktor.
Hello? Boleh ke? Okay. Sorry saya lupa nak pasang ni. Okay, we continue. So this is bending stress. Yeah, bending stress equation. Sigma equal to m over y. Okay. This is in last topic in bending stress distribution. Yeah. Y is the depth of the section. Yeah. Sigma equal to my over I, and this, what is this? Just for our knowledge, sigma equal to P over A is the axial force. This one is axial stress. Axial stress, and this one is bending stress. Yeah, bending stress, which zero at the centroidal axis. Yeah, and maximum at the most outer layer of the section. My over I. So this is important. So using this equation, yeah, therefore 1 over R equal to E over Y epsilon equal to sigma over yeah, EY equal to MY over EI Y. Okay. So therefore 1 over R equal to M over EI. Yeah. So now, which means we combine this equation, E equal to 1 over R and E and Y combined with the bending stress formula, and this is the result. So this is the derivation. So based on this derivation, we will start to proceed with the deflection based on curvature. Yeah, here. Okay. So again, we use the principle of slope and displacement. Yeah, through double integration from 1 over R equal to M over EI. Yeah, and this one mathematic. This one mathematic. Yeah, I'm not familiar with this one. The relationship between 1 over R. R is the curvature. Radius. R is the radius of curvature. The radius of curvature. Dy over dx is the slope. The slope at any point x from the reference point. And d squared y over dx squared is the rate of change of the slope, yeah, as compared to x. So this formula, yeah, it's quite difficult for us to memorize, yeah, but it's just for our information. And then, in the case of elastic curve, the slope dy dx is too small, and can be ignored. Why it is small? Yeah, because it is elastic curve. Elastic curve is not large. Yeah, it is not excessive deflection, very small deflection. In design, the allowable deflection is only 1 over 360, very small. Yeah, and if it is more than 1 over 360 of beam length, yeah, it is fail. Yeah, fail in design. Yeah, okay. So when it is very small, yeah, and remember, we just take a very short portion. Yeah, short portion. So that means dy dx is very small. When dy dx is small, therefore dy dx squared is equal to 0. Yeah, a 0.1, for example, 0.1. 0.1 squared, what is 0.1 squared? 0.1 squared is equal to 0.01. Yeah, 0.001. The answer is 0.1 squared. And it's very, very small. So, yeah, we end up with this formula: 1 over R is equal to d squared y over dx squared. Okay, so therefore, yeah, Since 1 over r is equal to m over ei, therefore m over ei is equal to d squared y over dx squared. Therefore, yeah, ei, bring it here, ei d squared y over dx equal to m. This is called moment equation. Okay, now if we integrate this formula, this equation, what we have here is integration dy dx ei theta y theta, because dy dx is the slope. Yeah, is the slope. Slope is the angle. Yeah, the angle of deflection is theta equal to, yeah, integration of m in relation to the x. Okay, plus c1. C1 is constant. And if we integrate again, yeah, we have dy dx. When dy dx is integrate, then we have y. Yeah, and we have c1x plus c2, and here we have two constant, c1 and c2, and this is called deflection equation. This one is called slope equation. Okay, so yeah, similar to what you have done in mathematics. Whenever we have a constant, we have to use boundary condition. Yeah, boundary condition. In this case, when we have two unknown, that means we need to have two boundary condition. Two unknown, two boundary condition. If you have two unknown, but you have only one boundary condition, it is not enough. So what are the boundary condition? Boundary condition. Okay. The boundary condition, yeah, difference in different case. For example, here, for simply supported beam, when x equal to 0, y is the deflection, y is the vertical deflection. When x0, y0, x equal to L, y equal to 0. Two boundary condition. Yeah? Okay. In this case, actually, if it is symmetrical loading and symmetrical beam, actually dy dx or theta at mid-span is equal to 0. Okay? So in this case, if it is symmetry, then we have three boundary condition. But we don't need three boundary condition because we have only two, yeah, unknown. So these two boundary condition is enough to solve the problem of C1 and C2. Here, this is cantilever or overhang beam. In this case, what is boundary condition? Yeah, you have to understand the shape of deflection. The shape of deflection. If you don't understand, yeah, and this is common sense. The shape of deflection. X equal to 0, y equal to 0. Yeah, y is the deflection of vertical deflection. And we also know that when x equal to L, the vertical deflection y is also equal to 0. At this point, yeah, we know that deflection is maximum. Yeah, but it is not useful. Yeah, boundary condition is normally where we know the equation. We know the value here. X equal to L, the value is equal to 0. This one, we know it is maximum, but we don't know the value. This one, at this point, the deflection is, the slope is 0, but we don't know at what point. Yeah, we know that the slope is 0, but we don't know at which point. So therefore, yeah, we use only these two boundary condition. Yeah. Okay. So what is dua dx? Yeah, as I mentioned just now, dua dx is somewhere here, but we don't know at what x. So it is not useful. Yeah. Hmm. And for cantilever, yeah, this is different from what in pin condition. At x equal to 0, y equal to 0, and also in the same point x equal to 0, theta is equal to 0, or dy dx is equal to 0. So we have two boundary conditions. And in here, we know that deflection is maximum, but we don't know what is the value. So yeah, it is not to be used in, cannot be used in our equation, boundary condition. Okay. Now, take for example, I go to example 2 first. I go to example 2 first. For those who follow through the lecture note, this is example 2. Okay. The cantilever beam shown in figure is subjected to a vertical load P at its end. Determine the equation of the elastic curve. EI is constant. Determine the equation of the elastic curve. What is meant by elastic curve? Yeah, is the slope. Yeah, is the slope. But you can also have the deflection. Yeah. Okay. Okay. So from the free body diagram, with M acting in the positive direction, so you from left, you go to right. From left, you go to right. So the sign convention is M equal to minus Px, which is mean that what? Yeah, anti-clockwise negative. Yeah, you are here now. Yeah, and what is in at your left? Yeah, what is at your left? Use the sign convention anti-clockwise negative minus Px. Okay. Uh, and integrating this moment, yeah, because we know that EI d squared y is equal to M. This one is equal to M. This is not shown here. This one actually M. Therefore, EI d squared y dx squared equal to minus Px. Integrating about y, about x, then you have Px squared over 2 plus C1, and integrating again, we have deflection. The first integration, we have slope. And the second integration, we have vertical deflection, y direction. This is the equation. So we have two equations. We have two equations with two unknown C1 and C2. Now, our next job is to solve the problem of what is C1 and C2. Again, what is 2? Equation 2 is slope deflection. Slope equation. Equation 3 is called deflection equation. Equation 1 is called moment equation. Okay. Now the boundary condition. The boundary condition is that dy dx equal to 0 at x equal to L here. What is dy dx? Slope. The slope is 0 because it is now horizontal. 0. And also at x equal to L, y is equal to 0. Therefore, you have two boundary conditions. Now you have two unknown from two equations. So if you have two boundary conditions, then you can solve the problem. Okay, so this is the equation. 0 at x equal to L, at x equal to L, yeah, slope equal to 0, therefore 0. Also, at x equal to L, yeah, at x equal to L, this one, okay, deflection is equal to 0, therefore here is 0. Now you have two equations. You have two unknown, okay, then you can solve the problem. From the first equation, you have C1, and from the second equation, yeah, substitute C1 into equation 2, then you have C2. Okay, finish. Yeah. So, and then substitute, yeah, C1 and C2 into this equation. What is C1? Yeah. C1 is equal to P squared L over 2. Yeah. So, yeah, substitute into the equation, this one. C2 equal to PL, yeah, to the power of 3 divided by 3. Yeah. Substitute into equation 3. Then this is the answer. Okay. So this is the slope equation. This one is the deflection equation. From this equation, what next? Yeah, from this equation, you can calculate the deflection and slope at any point along L, x distance from A. Here, why from A? Because why from A? Because here, yeah, your moment equation start from A or start from left, not from right. Actually, you can also derive the moment, yeah, start from the right. Yes, but you will end up with the same equation. Yeah. Okay. Yeah. That's the first example. Yeah. Uh, it is quite important. Actually, from here you can calculate what is the maximum deflection. Yeah. Normally in design, in construction, what we need to know is the maximum deflection. It's not the deflection or the slope, yeah, along this beam. No, the maximum. What is the maximum? So when it is maximum, yeah, when it is at A, where x equal to 0, therefore, yeah, you just yeah, you just change x 0 here, and you have y maximum. It's not shown here. I repeat, because no, in practice, we just want to know what is the maximum. The maximum is here at point A. Yeah, it is common sense. Maximum is at point A, where x equal to 0. So when x equal to 0, yeah, substitute x equal to 0 here, x equal to 0 here, yeah. Therefore, the answer is y equal to p over 6pi multiplied by 2l to the power of 3. Similar to slope. Yeah, in this case, slope at A is also maximum. So, yeah, you put x equal to 0, then slope is equal to PL squared divided by 2e. Yeah, I hope you can get it. Yeah, the first example. Okay. For this second example, uh, I go to this additional. This one additional. Yeah, it's not not shown in your lecture note. Okay. This is simply supported beam. with uniformly distributed load. Okay, in the last topic you have done shear force and bending moment. Yeah, and I hope you can still remember how to draw bending moment and shear force diagram. Yeah? Okay. Now in this topic is to calculate what is the deflection at any point or what is the maximum deflection at midspan. Okay, bending moment at any point x from A, yeah, x from A is equal to WL over 2x, yeah, clockwise positive minus WX squared over 2 anti-clockwise negative. Okay, integrate, yeah, integrate we have slope equation. Sorry. Uh, mx is equal to ei d squared y over dx squared. Okay, then integrate. The first integration, yeah, we got a slope equation. The second integration, yeah, we got here deflection equation. I hope you have no problem, when you are doing the integration, okay. So I don't have to teach mathematics, assuming that you are familiar with the integration. So we have now two, we have now two what boundary condition, two boundary condition, and therefore we need two equation. As essentially, we have two constant unknown, then we need to have two boundary condition. What are the boundary condition? X equal to 0, y equal to 0, x equal to L, y equal to 0. X equal to 0, L, y equal to 0, x equal to L at B, y also equal to 0. And for this symmetry, for this symmetrical equation, symmetrical deflection, symmetrical loading and deflection, we also know that at midspan dy dx equal to 0. Can you understand? The slope, the slope is equal to 0. But we need only two boundary condition. So using these two boundary condition, we have here Ey equal to 0 equal to C2. Therefore, C2 equal to 0. What is this? From this equation. Substitute x equal to 0, 0 here. Therefore, C2 is equal to 0 because y is equal to 0. Okay. And then the second boundary condition is y equal to 0, but L, x equal to L. So when x equal to L, what is C1? C1 is equal to here. Here. And then C1 is equal to here. Okay. Then, bring L, to here, cancel. Then you got here L to the power minus to the power of 3 here. Therefore, the equation now is equal to EI, Y, WL, and so on. So this is the equation of deflection along the beam X from A, or in this case, X from any end, from A or from B, because it is symmetry. What is the maximum? So this important. This formula is important, but this is not the final. Our main purpose is to calculate what is the maximum deflection at midpoint. Why at midpoint? Because we know, for this symmetrical deflection, symmetrical loading, symmetrical structure, the maximum deflection must occur at midspan, not at any other point. And again, I repeat, this maximum deflection will be checked with the design requirement. Design requirement is the international requirement we cannot run away from the requirement. So at x equal to L over T, L over 2, yeah, substitute x, yeah, with L over 2, L over 2, L over 2 there, yeah, then EIY equal to 5WL to the power of 4 divided by 3 and 4, which becomes another formula or another equation deflection value that you have to, I can say, memorize. Yeah. Because in many cases, yeah, in many cases, yeah, in practice, the load is uniform. Load is uniform. Yeah, and also, yeah, the structure is also symmetry. Symmetry means pin here, pin here. So the deflection is symmetry. Then this is the formula that you have to remember. Yeah, you have to remember throughout your life, yeah, for the rest of your life. And actually, I have another example. Another example. Point load at mid. Yeah, point load at midpoint. This is another important. Yeah, but I have not uploaded into the PowerPoint. I have it in Word. So I hope you can understand understand this one. And we go back to the example one now. Yeah. Uh, okay. Determine the midspan deflection of beam shown below. Yeah. I go through this example and then we take 5 minutes break. Is it okay? But in this online, I think if you want to take break yourself, I can also, yeah, cannot see you. Okay, determine midspan deflection of beam. E equal to 20, I equal to 1/600. Yeah. In the example 1 and example 2, there is no value. Yeah, there is no value. The deflection is only in term of E and I. And now, yeah, we have value. When you have value, that means the deflection will be, yeah, in millimeter. Okay. 18 kilonewton, 2 meter from A. A and C simply supported. Yeah. In this case, A is pin, C is roller. Okay. But even if C is pin, the solution, the calculation is also the similar. Also, if it is roller and it is roller, what happened? Also same calculation, but the structure is called not stable. Yeah. If it is roller and roller, it can move. Yeah. Freely move. Yeah. Like trolley. Yeah. Or like what? A skateboard. So it is not stable. But we can, theoretically, we can calculate the deflection. Okay. Now, yeah, our first task is what? Reaction. Because, yeah, to derive the moment equation, you need to know the deflection. The reaction. Okay, so this is the conventional method. Yeah, I call it conventional, or yeah, the long method. The short method is this one. Short method. But if you are not familiar, yeah, you have to use this method. Okay. Actually, this is not different method. The same method. The same method. Actually accepted or summarized from this method. Okay. What is this? I don't want to tell a story about this one. Because it is common. This one. I have given this formula during in the last topic on thrust. On thrust. RA equal to 18 multiplied by 4/6. What is 4/6? Yeah. A 18 multiplied by the longer segment divided by the total span. And C, as we know, because C is at the farthest, longer or farthest point from 18, therefore, reaction here should be smaller than A. A is bigger reaction because 18 is close to A. Yeah. Therefore, we have this common sense. So, RC equal to 18 minus 12, or RC equal to 18 multiplied by the shortest distance divided by the longest distance. This is just by proportion. Yeah, by proportion. So, yeah, in exam or in a test, if you use this calculation, it will takes you time. But if you use this equation, very short. And when you becomes engineer, you cannot use this equation. You must use this equation. Okay, unless if there are another loading. Or 1, 2, 3. You cannot use this equation. If you have only one equation, one loading, you can use this equation. Okay. Now, can you derive moment? Derive one single moment equation between A and C. You can try at home. Try to derive a single moment equation between A and C. You will find you cannot derive that formula. Because why? When you are here, the moment is equation is equal to RA or 12 multiplied by X. But when you are in between B and C, the moment equation is equal to RA X minus 18. So you have two different equations. When you have two different equations, how to interpret? Cannot. So you have to split into two segments, segment AB and segment BC. Segment AB and segment BC. Here. Okay. Now you will have two equations. You will have two equations. Okay. So now treat this equation separately. As I show you here separately. This one is for segment AB. This one for segment BC. For segment AB, moment equation, slope equation, and what? Deflection equation. For segment BC, moment equation, slope equation, deflection equation. Okay. And yes, now we have what? We have equation 1 and equation 2 for deflection. 1 and 2 for deflection. And you notice here, in previous example, we have two unknown or two constant. But now because we have two segments, two unknown for segment 1, two unknown for another segment. So if you have four unknown or constant, that means you have to find four boundary condition. Okay, four boundary condition. What are that boundary condition? Here. Okay. What are the four boundary condition? The first boundary condition is x equal to 0, y equal to 0. Here, deflection 0. The second boundary condition is that x equal to 6 meter and y equal to 0. Another boundary condition, you see here, when x equal to 2 here, when x equal to, the deflection for segment AB is equal to deflection for segment BC. What I mean here is that then from boundary condition, you have 4 unknown, then here, this is matching condition here. Then, you solve the equation, I don't have to go detail, this one is a mathematical. The end result is that, y equal to 1 over EI, 2x power of 3 minus 40x for segment 1, and y equal to this equation for segment 2. What happens if x equal to 2? When x equal to 2, if you substitute x equal to 2 here, and if you substitute x equal to 2 here, it will give, this both equation will give the same value. That's what we call compatibility or matching condition. Okay. No question, but in this case, what is the question? The question is determine the midspan. The midspan means this one. When x equal to 3. So what should we do? Just substitute or replace x equal to 3 for the equation, and then this is the value. Okay, substitute x equal to 3 to which equation? Is it equation for segment 1 or segment 2? Equation for segment 2, because x equal to 3. 3 is in between 2 and 6. We cannot substitute into equation 1 or into segment 1, because this one is only for x between 0 and 2. Okay, if you substitute x equal to 3 here, I don't know what happened. It will give you crazy answer. Okay, minus 2.16 millimeter. Why? When it is minus, this is indication of downward deflection. Okay, so this is about double integration method. Okay, we'll have a 5 minutes break before we go to another method, Macaulay method. Macaulay method. 5 minutes. Okay.